Kalimera Alada. My name is Jamie Coleman. I'm here today to talk to you about some simple tweaks you can make to your JVM to get the best performance out of your applications. I do speak a little Greek and mostly swear words, so if you have anything bad to say, don't say it around me because I will know what you're saying. So let's get started. So just to clarify who I am. I'm a developer advocate for IBM. I've mostly worked in open source Java technologies, started on containers and then moving to runtimes and things like that. The things I want to talk to you about today are, first of all, what is a JVM and why is it important? Because me as a developer, I use the JVM a lot, but I don't really know the ins and outs of how it works. I'm going to talk about how the cloud has changed the JVM over the years. Then I'll move on to some of the most used JVMs that we use nowadays. Then I'm going to talk about how the runtime you use is important. Then we'll move on to the main topic of this talk, which is tweaking your JVM. Then I'm going to hopefully talk about some specific OpenJ9 technologies that are present in some of the other JVM releases. And hopefully I'll provide you a demo today, providing the demo gods are happy. And then I'll move on to some technologies which hopefully that are coming out in the future, which will even help us even more. So let's get started. Like I said, why the JVM is important. Well, without the JVM, we wouldn't have Java as we know it today. So what does the JVM do? Well, the JVM is a Java virtual machine, hence the phrase JVM, and it's responsible for taking your application bytecode and converting it into a machine language for execution. Most other languages compile code for a specific system, but in Java, the compiler converts the code for the Java virtual machine that can be used on any system, hence the phrase in Java, write once, run anywhere. So why do people use JVMs in Java? Well, it's cross-platform, like I said, write once, run anywhere. It's got a large library ecosystem because Java's been around for a while. It's got a great garbage collector, so it handles everything you're not using anymore to clear it up and free up memory. It's got some really powerful monitoring tools, and it's proven and robust. Java's been around for a long time, lots and lots of applications, and enterprises use it around the world. So that's why we're all here today, and we're still using Java, so it's awesome. So again, I am a software engineer, but I use a JVM all the time, but I don't work on JVM architecture. So I was quite intrigued of how the JVM works, hence why I created this talk. So with the JVM, you kind of have three levels. You have the class loader subsystem, then you have the runtime data area, and then you have essentially the execution layer. So the class loader subsystem, what does it do? Well, you have three kind of things. You have loading. Loading loads classes using three different class loaders, bootstrap, extension, and the application class loaders. Then you have linking, which verifies the generated bytecode, prepares all the static variables, and assigns default values and resolves all some symbolic memory references. And then you have initialization, which essentially assigns static variables with their original values and executes the static block. So then moving on to the runtime data area. This basically you have the method area which stores metadata, the constant runtime pool and the code for your methods. Then you have the heap, which is common memory shared between multiple threads, and that stores things like objects, instant variables and arrays. Then the Jvm Language Stack, this is created when a thread is created and stores local variables. PC registers, this is every thread that's created has its own register, and this stores the address of the Java virtual machine instruction which is currently executing. And then moving on to the native method stack, and this holds native method information. So for every thread that's created, so is a native method stack. So then finally onto the execution engine. This essentially, the execution engine reads the bytecode and executes it using either the interpreter and the JIT compiler. The native method interface, JNI, this interacts with the native method libraries to provide the required libraries for the execution engine. And then finally, the native method libraries, this is just a collection of native libraries. So now you're all pros in how JVMs work. How has the JVM changed over time? And how has the cloud changed the characteristics of the JVM? Well, first of all, what drives the world? Money, of course. So cloud, if we think of cloud computing, we're thinking of money, but I try and change this. So developers, money doesn't mean that much to us. We're working for big organizations or any organization. And yes, it's nice to save our organization some money, but at the end of the day, it means not so much to us whether we save our organization $100 here, 100 euros here, 1,000 euros here. Whereas if you think of this as in terms of energy, so data center providers, they essentially, their biggest cost, obviously once they've set everything up, is their energy consumption. That is their biggest cost. So by you reducing the amount of resources you're using on the cloud, and making your applications more efficient, you're essentially saving energy around the world. So don't always think about this as money, as a lot of people talk about it. Think about it as energy. So what the cloud offers, okay, imagine this is your local data center in your organization, and the problem is we need hardware to essentially keep up with peak demand at all the time. So if we move to the cloud, as you can see now, we can free up some of those resources for other people around the world to use, hopefully saving some energy as well. And then if we move to kind of a smaller architecture like microservices, we can free up even more resources for people to use. Now, moving to a microservice architecture has its problems, especially with Java. So it's okay when a JVM is really designed to run lots and lots of Java applications, but when we've got lots of microservices, each one of those needs a JVM, which is a big chunk of the stack. And if we've got all these JVMs, which really were intended to run lots and lots of applications on one JVM, now we've got quite a big overhead. So a lot of the people that create JVMs all kind of went back to the drawing board here and tried to figure out the best characteristics they could get from their JVM in this new kind of microservice world. So the key performance metrics that we're measuring here are startup time, ramp-up time, memory footprint, response time, and CPU and throughput. But when you make changes to these characteristics, they can have detrimental effects on the other characteristics. For example, if I reduce my startup time dramatically, I could have problems with throughput. So yeah, it's great my application can start up really, really quickly, but if it can only handle half the throughput that another JVM could with double the startup time, then it's not really that useful. So it's a constant battle with the people that are creating these JVMs to get the right characteristics we need in today's world. So hands up, who remembers this phone? Yes, very good. Yeah, amazing phone. You can throw it at a wall, it would survive. I'm pretty sure I've dropped one from a second floor and it survived. That was actually in Cyprus, funny enough. But yeah, so amazing phone. But this phone, it was using something called Jvm. So if we look at the characteristics of Jvm, well, we have things like small footprint, fast startup, and we want quick immediate ramp-up time. Now, the difference is with this hardware was limited. It was the hardware that was limited, whereas now in the cloud, we're not limited by the hardware, but we're limited by the cost and the amount of energy we're using. Again, remember, trying to consider energy here. So if we compare these characteristics to the JVMs in the cloud, they're pretty similar. You've got small footprints, fast startup, and quick immediate ramp-up. Again, we want a small footprint because we don't want to be using lots of memory. We want fast startup because the time it takes our applications to start up is pretty much wasted time, and we want it to ramp up quickly. So imagine if you're playing Snake on the old Nokia. If you had to wait 2 or 3 minutes by the time that game was running properly, then you'd probably not play it as much, right? If you were playing Call of Duty or something like that, if you had to wait 5 minutes before it stopped jittering, you wouldn't play the game for very long. So immediate ramp up and things like that are very, very important, especially for our applications as well. So again, going back to the energy thing, why should developers care about optimizing our applications and getting the best performance out of them as possible? So throwing you some facts here about data centers. So there's 500,000 data centers in the world. This information is from 2019, so it's probably a lot more nowadays. The land they consume is around the same size as 6,000 football pitches. And if you compare the amount of energy these data centers use, remember, we don't see these data centers. The public probably doesn't even know most of them exist. They're using Facebook, etc., blah, 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 which are using huge amounts of energy in the back end. So if you take the UK's energy consumption and times that by 1.5, that is what data centers around the world are using. And that was in 2019. So it's probably more like 2 times the UK's energy consumption now. Now, luckily, if we've got any friends that are in the hardware industry, they have been doing their part. Hardware efficiency has dramatically reduced the amount of energy we're using on hardware these days. So at this graph, if you look at the line going up like that, that is pretty much where we would be if the hardware engineers hadn't done their part. But we're all engineers here, and if someone's going to save the world, it's going to be engineers. So we have to kind of do our part here as software engineers to make our applications as efficient as possible so we can keep that curve as low as possible. So now I'm going to give you a little bit information about some of the JVMs that are possible. There's pretty much a JVM for everything out there. Some great name JVMs like Wonka JVM, Quark JVM, etc. And so they range from things like running on IoT devices, embedded devices, all the way up to full-blown JVMs that we use. The Maxim Jvm is quite a particularly interesting one. This was created by Manchester University, and it later is what became GraalVM, which a lot of you may know. So the most popular JVMs there are Oracle's JDK, of course, the different flavors of OpenJDK. Azul's got their own one, you've got Graal, and of course you've got Eclipse OpenJ9, which is now IBM Semeru runtimes. So I'll talk about 3 of those JVMs. I'm not going to go through all of them because, yeah, there's a lot of information there. So Hotspot, formerly known as Java Hotspot Performance Engine, hence why it's called Hotspot. This was created by Sun, which is now Oracle, and this was the main JVM in Java 1.3. And so in 2006, the Hotspot Jvm and the Java development kit became open source. And this is really what paved the way for having all these different flavors of JVM that we have today. So thank you, Oracle, for doing that. And essentially, the reason it's called Hotspot, because it analyzes your code for anything that's executed repeatedly, called hotspots, and it optimizes them as much as possible. So that's really why it's called the Hotspot Jvm. Moving on to OpenJ9. So who's heard of OpenJ9 here? Anybody? A few people. Awesome. Okay, so this was IBM's Java. It's been IBM's JVM for over 25 years. It was open sourced just over 5 years ago. I think it's had its open source birthday about 5 years ago in a couple of weeks. And this is really designed to span all different IBM products. So it means all different architectures, all the way from a mainframe to ARM architecture. Basically, it has to span every kind of architecture. It can go from small to large, so there's very small versions of this JVM and very big ones, and it can handle constrained environments really well, and I'll talk a little bit more about that later. And like I said, it's used by some of the largest enterprises on the planet, so it is a very, very robust JVM. Here's some stats. This is from the OpenJ9 website, comparing it to Hotspot. As you can see, it's nearly double half the startup time, nearly half the footprint of the Hotspot JVM. The ramp-up time's much faster, and like I said, that's very important because the time it takes our application to start up is pretty much wasted resources. And it's got a smaller footprint on load. So we want our JVMs to be as performant as possible when under load, and that's what the OpenJ9 JVM tries to do. So a little overview of GraalVM. So this is based on the Hotspot OpenJDK with roots, like I said, in the Maxim virtual machine. And this was developed by Sun and Oracle and the University of Manchester in the UK. So why is this JVM or different to the other JVMs? Well, it has a new JIT compiler, the GraalVM compiler. It allows ahead-of-time compilation of your Java applications, and it basically has truffle language support, so it means it supports lots of different languages. And it's got an LLVM compiler, and it's also a JavaScript runtime, which is awesome. So the main project goals of GraalVM are to improve the performance of our Java virtual machine-based languages to match native languages. We want to reduce the startup time of JVM-based applications by compiling them ahead of time. We want to enable GraalVM integration into lots of different things like Oracle Database, etc., Node.js, blah, blah, blah. It allows the freedom of mixing of code from different languages, polyglot applications, and it includes an extended set of polyglot programming tools, so trying to make it as developer-friendly as possible. Now, you may all think GraalVM is amazing, but it has its downsides compared to a full-blown JVM. One of the most notable things is throughput. So if you, a JIT compiler, JVM running JIT is very, very efficient at what it does. So if you've got applications that are supposed to be stood up for a long time and require a massive amount of throughput, then GraalVM might not be what you need. But if you need things that are really fast starting, so if you've got an architecture like function as a service where you want it to kind of come up, do what it needs to do, shut back down again, then that's when GraalVM really shines. So now moving on to runtimes, because it doesn't matter if you have the most efficient JVM possible, if you have the most efficient code possible, if you are using a runtime which is not efficient and not designed for what you're trying to do, then all that effort is going to be wasted. So the two runtimes I'm going to talk to you today are, one is from IBM and the other one is from Red Hat. Of course, I'm biased here being from IBM. So I'm going to talk about OpenLiberty. So another thing, hands up, who's heard of OpenLiberty before? Ah, cool, that's good. So OpenLiberty was open sourced about, again, same with OpenJ9, just over 5 years ago. And OpenLiberty's goals were kind of to be developer friendly. So who's heard of WebSphere here? I presume a lot more people have heard of WebSphere, right? So the thing with WebSphere is we have a customer that has been running a WebSphere application server for over 10 years without shutting it down. So that just kind of shows you how robust that kind of application server is. But it's not really geared for the way we run things today. Having an application server that's 2 gigabytes in size, very complicated to administer, it takes a long time to boot up. I'm a developer, I want to test my code instantly. I don't want to wait 10 minutes to test my code. And that's kind of where we went back to the drawing board and created Open Liberty. So focusing on making it as developer friendly as possible. So just enough runtime, so it's modular, fast in a loop, so you can make changes to your code, your configuration, and your tests without having to restart the application server. Support for all the industry standard dev tools. Support for things like Jakarta EE, Java EE, Microprofile, and Spring. I don't talk about Spring much in this talk, but using Open Liberty, say over Tomcat with Spring, provides you nearly double the throughput. So if you think about that on the cloud, if I've got an microservice that has double the throughput of another microservice, I should need half the amount of microservices. Now, there are downsides of that. I think the boot up time is slightly slower, but if you don't care about that extra second or two startup time, then having better throughput would make a lot more sense. And zero migration. So this is very, very important to us because we have customers that are using versions of our stuff that is like 5-10 years old. And the problem with that is it takes a lot of effort to move up to the latest version, whereas with Open Liberty, we essentially wanted you to be able to take your application code, use the latest version of the runtime so you can get all the goodness, all the new functionality and the features, because we have 300 developers working on this in IBM. And we want you to be able to move your code up to the latest version without it breaking. So zero migration has been at the heart of this project from the beginning. And it's cloud ready. So the first job I did was actually containerizing Open Liberty it was Liberty, but yeah, containerizing Liberty at IBM when I first started. I mean, coming out of university 9 years ago, I had no idea what a container was. I was dumped in a team and said, right, you've got to containerize this, build a DevOps pipeline to issue these releases. So that was one of the first things I did, and I think it was one of the first products of IBM to actually be containerized. So it's very, very efficient in containers. It's designed for DevOps. It's got a very small disk footprint, very efficient memory usage. Again, fast startup is something we've tried to do as much as possible. Again, going back to the throughput thing, the throughput has been a very key thing here. We want our users to have the highest throughput and to allow as many users to access their application on one microservice as possible. And it's got a self-tuned thread pool, so it handles all the thread pool by itself, so you don't have to care about that. Like I mentioned, it's just enough runtime, so comparing to things like WebSphere Traditional, where you've got everything you need in one box, this is modular. So you start off with nothing, and you include the functionality and the features you need building the runtime you actually require. API support, we've been trying our hardest to be certified for every new one of these releases. So in our development organization, when one of these releases come out, it's panic mode. Everyone's full on trying to certify for it. And we have been the first to certify for Java EE 8, Jakarta EE 8, Jakarta EE 9, Eclipse Microprofile 1, 2, 3, 4.1, and 5. So we've tried really, really hard to be the first runtime to certify for these. Okay, now moving on to Quarkus. I presume a lot of you have already heard of Quarkus. I know there's been lots of talks around it at the conference. So Quarkus is amazing. It's got unified configuration, zero config and live reload, just like Open Liberty. Streamlined code for 80% of most common usages. Again, and this can take advantage of GraalVM. So if you really are focused on how quick you want your application to start up, this is a really good runtime for that. And it supports many libraries, one of them being Microprofile and of course Spring and others. So some stats about Quarkus, you've probably seen this graph before, but Quarkus is really, really amazing with GraalVM in terms of startup time. And it's really great for architectures like function as a service, where you need something to start up rapidly, do its job, and shut down. But there's lots and lots of different runtimes available. So it's very, very important you pick the right runtime for the application you're building. Because no matter how performant your code is, no matter how good the JVM is and what characteristics it's got, if you're using the wrong runtime for what you're trying to do, your application is not going to be very efficient, and you're going to consume way more resources, energy, and spend loads more money on the cloud than you actually need to. And the thing is, these days, all this stuff is open source, so there's no excuse for you to try out different runtimes to see what actually is performing better with your applications. Okay, moving on to tweaking the JVM. So how do we make the most of our JVM? Again, it's something I use and we all probably use, but none of us, well, most of us probably don't go into the ins and outs of how the JVM work and how we can tweak it to perform better. Well, first of all, writing efficient code, not tweaking the JVM, but if you've got an efficient code, doesn't matter what tweaks you make to your JVM, your application is not going to be very efficient. Using the right JVM for your needs, like I mentioned, picking a runtime that's right for your application is key. Using profiling, which is something I've not done a lot with JVMs, but it allows you to look deep inside your JVM and see what's going on. And then tweak your JVM depending on the needs in development and production, because you don't forget you have different needs in development than you will in production. So writing efficient code, use primitives where possible. Using things like a string builder rather than a string buffer is more efficient. Avoid using an iterator. Now, this is, you know, that's debatable, but basically what I'm saying is if you can avoid using one, avoid using one. Don't get me wrong, there's lots of use cases where you can't, but if you can, try to do it. Avoid using things like big integer and big decimal. If you don't need that variable, don't use it. It uses so much more resources in the JVM than if you just use an integer or something. So when you're writing code, think about what you're using and if it's required for what you're trying to create. So again, back to using the right JVM for your needs. There's lots of JVMs out there. Again, I'm talking a little bit about IBM Summary Runtimes, which is based on OpenJ9. And again, this was open sourced about just over 5 years ago. And you can, if you want, get license for it if you need to. And you can find all that license information on some of these links here. And you can get license also through Red Hat if you need to. So the best place to look for JVMs is the Adoptium Marketplace. This is where you can see all the different JVMs and get what you need. And again, do your research. Look at the JVMs, their characteristics. Look at the goals of those projects and what they're trying to achieve and see if they fit in with what you're trying to create. So going back to the runtime thing, this is kind of a little architecture graph I have here. You'll see something called a macro service. So it's a bit of a debatable term, but so a macro service is not a distributed monolith. A distributed monolith is what I'd say is a well-architected monolith. A macro service, I find, is where people try and take apart a monolith, they try and break it into microservices, and then they realize some of the services are so highly coupled together, they'd have to rewrite all those services. So rather than do that, they essentially couple those services together. So you have bigger services, not quite monoliths, so you've got your application split up into lots of parts, but you have slightly bigger services. So where you've got high coupling and it makes sense to scale those things at the same time, that's what I mean when I say macro service. So as you can see, this is where Quarkus fits in really well with function as a service up to microservices. Open Liberty, we try and be the JVM for everything really. So spanning from microservices all the way to monoliths. Open Liberty has the same functionality as traditional, but it has it in a way where it's very, very performant. So trying to span all those different architectures is a difficult task for our development team, but they do it very well. Profiling, like I mentioned, Java profiles are really useful tools, and they can enable you to monitor Java bytecode constructs and essentially look at what the hell is going on inside your JVM. I was quite blown away when I first started using some of these tools. And some of the most things, so you've got garbage collection, it can look at garbage collections, object creation, method executions, all kinds of things. So if you've never used a profiling tool, I suggest to test one out. Some of the most popular ones are things like JProfiler, YourKit, Java, Visual VM, NetBeans Profiler, and if you're using the Oracle JDK, there's Oracle Java Mission Control. So back to tweaking your JVM. First of all, a good thing to do is to tune your garbage collector to make it as efficient as possible. Make sure you're using the things like @InTime compiler. That can reduce your startup time dramatically. Enable things like class data sharing or class cache sharing as we talk about it in OpenJ9, and I'll hopefully show you a small demo of that in a moment. We're going to enable idle tuning, and I'll talk a little bit about what that is, and using a JIT server, which is quite important. And I'll talk about those 3 different things in a moment. And also with your heap size, start with as smallest heap size as you can imagine. Now, don't make it too small because your application won't work, but start with something a bit smaller than what you're used to. If your application starts to run out of memory, just start increasing it, etc. But if you start with a massive heap size, you're going to be consuming more resources than you need. So OpenJ9 class data sharing, what is this? So this is something that OpenJ9 has put in its JVM, and Open Liberty has had some changes as well to make the most of this. So what it does is use a shared class cache in an area of shared memory of a fixed size, and basically it persists beyond the lifetime of your JVM. So if you shut down your operating system, etc., this class cache will stay there. Like I said, it's a fixed size, so it can't grow, but you can make it bigger. But if it becomes full, don't worry, nothing's going to break. It just won't add extra classes to the class cache here. And you can create a large and small class cache up front, basically you just have to change something on the Linux operating system to do that. So how does it work? So traditionally, a JVM will go to the class loader cache first, then the parent, and then the file system. In contrast, a JVM with class cache sharing will go the class loader cache, the parent, then it will go to the shared classes cache, then the file system. And this basically, all the classes you use on startup that you need immediately are in this shared class. So rather than going through the whole file system to find those classes, they're in this shared class cache, which makes starting up very, very quickly. It's very, very simple to get started with this. With OpenLiberty, I'll show you hopefully how to do that in a moment, but essentially all you need to add is the JVM option of X shared classes. You can give it a name if you want different shared class caches for different applications. So if you're using a JVM for lots of applications, you can give it different names, or you can just use, like I said, X shared classes, and it'll just run for all of them. And again, if you want to specify the size of your JVM, you can use the parameter at the bottom of this slide here. So I'll show you some comparisons with this technology enabled. So this is OpenLiberty and some other popular runtimes with Hotspot Jvm without shared class cache enabled. And as you can see, OpenLiberty startup time is halved with that. And this doesn't just apply to OpenLiberty. All the other runtimes here, yes, they haven't had as much dramatic changes as they did as OpenLiberty, and that's because changes have gone into OpenLiberty to take advantage of this, but there are still savings there. And imagine if we all made these small savings, how much energy, because there's like 40 million or something crazy Java applications running around the world. Imagine if we made these tiny little changes to our JVM, how much energy we could save. And it's not just, running on bare metal, etc. You get these these savings in containers as well, which is important because a lot of us are using containers these days. So again, a lot of changes have gone into OpenJ9 and OpenLiberty. That is because obviously OpenLiberty is an IBM product, and OpenJ9 used to be. So there's a bit of influence there where we can get changes in that will really make the most of this technology. So I'm going to try and give you a quick demo. I know I've only got 10 minutes left, so I might have to quickly pace through this very quickly. So I'm using essentially an online environment. So if you went to my colleague Grace's talk yesterday, she showed you a very quick overview of this environment. Essentially, this environment was created because the amount of conferences I go to where I run a workshop and people don't have the right version of Maven, they might not have Docker support, etc. So we wanted to create an environment where everyone can come and try this out. If you want to try this out with me, you're welcome to. Essentially, just go to the OpenLiberty website, go to any one of our guides that has running clouds, click on that, click on running clouds, and it'll take you here. And then you get into the environment. Now, we didn't have a barrier to entry to this. It's a bit flickery. Okay, I apologize. We didn't have a barrier to entry originally with this environment, but as you may know, people like to take advantage of free resources on the internet. And we noticed very, very quickly that was happening. So you do have to log in, but that is the main reason for that was pretty much just because people were abusing our free resources. Right, so let me go into the finished directory. We're not doing this guide today. I'm just using this sample application from this guide to show class cache sharing. So what I'm going to do, the finished directory, there's two directories in all our guides. The start is where you would generally start with the tutorial, and finish is the application you're trying to end up with. So what I'm going to do is I'm going to start Liberty. Without class cache sharing on, anything like that. We're going to see how long it takes to boot up, and then I'm going to enable it, and we're going to see, hopefully, if everything works properly, that we should see some performance benefits in terms of startup. First time this starts up, it's got to download a load of stuff from Maven, so yeah, just bear with me for that one. But while it's doing that, I'm going to go and create the file I need to essentially enable this. So in our file structure here with Liberty, we have a config folder. Basically, that is loaded when we start up the application server. So in here, I'm going to create a file, jvm.options, and this file basically, will basically pass in any JVM options I put in the file to the JVM when the application starts to boot up. So we've got our file here. Give it a second to, actually, I might as well just share classes. Oh, actually, no, I won't do that because it auto-saves, and I don't want it to do that in the middle of starting up. Okay, so our application started up, as you can see down here. Oh, yeah, I am showing it, in 10 seconds. So now I'm going to enable this, share classes. Yep. That's automatically saved. And what I'm going to do is shut down the application server and restart it again. Now, the first time generally you run this, it has to do a bit of populating of the shared class cache. And then the second time we run it, that should be loaded. And then we should get the performance benefits. So we'll just wait for this to start up very, very quickly. I know I've already got 8 minutes left, so I'll try and be as quick as possible. Come on, come on, come on. And then, yeah, hopefully we should see a good improvement in the startup time. So now we're down to 1.6 seconds. Now, I'm very debatable whether it will actually get lower than that. But essentially, the more you run this, the more it trains the class cache. So if you run it over and over again, you should slowly see more and more performance benefits. Now, there is a limit to that, obviously. It's not going to go down to 0. But for OpenLiberty, bear in mind, this is a learning environment running on OpenShift in the IBM cloud. And the fact we've gone from, 10 seconds down to 1.4 second startup. Imagine if we made these changes to all our applications. We could save a lot of resources around the world. So let me just go back to my presentation and I will try and finish everything up as quick as possible. Okay, so idle tuning, I briefly touched on that, so I'll try and explain what that is. So idle tuning essentially allows you to save resources when your application is not doing anything. So this is a graph showing where idle tuning is enabled, there's no throughput, and as you can see, it's saving some resources. Now, okay, that's not going to save us any money. It's not going to save our organizations any money because, well, unless we own the hardware, but if we're renting hardware, we buy it in compute units. So it's not going to save us money, but it will save energy. And again, that's something that's important to me. It's not so important, saving our organizations money. Yeah, that's great. We do want to do that. But saving energy is really important. And as engineers, we really need to try and do that as much as possible. So introducing the JIT server, what the JIT server is, it essentially allows you, and you can run it in a separate container. And basically what happens is if you have a constrained environment, the JIT server will allow you to keep essentially running. So if you run out of memory, and the problem is nowadays we have these compute units and they're a single block of memory and they can run out. We have memory leaks, etc. So we don't want, if that happens, for our applications to crash. So here you can see we've got a unit, 300 megabytes. This is OpenJ9 and OpenJ9 running with the JIT server. So we've got about the same throughput there, perfect. We drop 50 meg. Now you can see it's still fine, but it's starting to struggle a little bit. We drop another 50 meg, and without JIT server, our throughput has crashed, which means our users won't be able to access those applications. Whereas with the JIT server running, hopefully we would have some monitoring tools running which would go beep, 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 very quickly, tell us to run and fix this problem. Whereas the other alternative is it just breaks. So it's very good when you're in these constrained environments, when you're buying specific amounts of memory on a cloud. So if stuff does go wrong, you can basically, it gives you time to recover. And so your users hopefully don't have any downtime. There's also a container density graph here. In the interest of time, I'm not going to go into this in too much detail, but it basically suggests that we did some research and tried to use the JIT server. Using stuff without a JIT server and then using it, and we're actually getting better density with our application. So this is a mixture of lots of different applications here, but we're actually getting better density and better value for our money using the JIT server than not using it. And if you want to find out any more information about this, just let me know and I'll point you to the research. It's very, very simple to enable. Again, you just need to use the following command to start the JIT server, and then, to connect to your JIT server, and then you can use the other command to just basically point it to that. So very simple to get started with. Right, just to finish off with the last 4 minutes we've got, is there any future tech to the rescue that can help these JVMs respond even faster? So I know there's lots of different, there's a couple of technologies around this. The one I'm talking about is Instant On. This is based on CRYU, which stands for Create and Restore User Space in Time. And essentially, it's a functionality that's built into the Linux operating system. And what this allows us to do is to basically build our applications, create a kind of checkpoint of where we want it to start and stop. And that allows us to shut our applications down and then start them up very, very quickly. So it's really, really good if you need that really fast startup time, but you need the functionality of a full-blown JVM. As you can see, the bigger the application you have, the more savings you get with this technology. So as you can see, going from like 5 seconds down to 0.2 seconds on the biggest technology stack we have here. So it's really, really useful if you have these applications that you can't make really small, but you want to get the startup performance that you could with, say, native compiling. So it's really, really good technology for that. And if you want to know more about this technology, again, just reach out to me afterwards, and I'd be more than willing to help you there. So just a quick recap to end things. So what have you learned, if anything, today? So basically, writing efficient code is very important. That is the first thing that we should all try and do as much as possible. Then we need to look at what different JVMs are available and what applications we're trying to build to get the best stack and the most performant stack. Then we need to pick a runtime that is right for our application. And then use things like profiling, etc. And, look at the options of tweaking your JVM. Look at the JVM you're using, look at the functionality it has, and see how you can use that functionality to get the best performance out of your applications. And again, the less money we spend on the cloud, just, something to think about, the less energy we're using. So trying to save as much energy as possible. If you want, I will put this presentation online, but here's some of the links to some of the materials I have talked about today. If you want to know some information about some of the references and the research I've done for this talk, because again, I'm not an expert in JVMs, this is just something that really, really interests me, then you can find all that information on these links. And just something to kind of end with, this is something I spotted on LinkedIn, which I thought was quite cool. It's research on the greenest languages that are out there. And guess what? Java's in the top 5, yeah, even though it's 25, etc. years old. So Java is still a great choice for the cloud. It's still a great choice for performant applications and saving energy. So keep doing what you're doing, Java developers. And yeah, thank you for listening to my talk today. Enjoy the conference. Thank you. Oh, before you go, let me take a picture just to prove that I've actually done some work since I've been in Athens, because, yeah. Thank you, everybody.